Okay, so now I've got these runners here, and I've got miles run per week, and I've got 8 runners, so my N is equal to 8. So I'm going to use my formula here, and I'm going to come over here to the slide, and I'm going to go step by step. I'm going to have to find my average, which is the sum of x divided by 8 in this particular example. So step 2 is find the deviation for each value. And the deviation scores are going to be my mean. Mu is 11.75, so I've added all these up. These are the number of miles run per week is in this category right here. So I got runner 1, 2 miles, 4 miles, 7 miles, 10, 15, 18, 18, and 20. I summed all those up and it was 94, and I'm going to divide by the number of runners I have, which is 8. Now I've got that, I've done that. I found my mean over here, which is 11.75. So I'm going to put 11.75 into each one of these little categories, and I'm going to subtract the mean from each score. And when I do that, I'm going to get what's called a deviation score in this category here. So remember what I said is that deviation scores are going to deviate to the negative side of the distribution and the positive side. And the mean is going to split that positive and negative values of a distribution. So now what I've done is I've taken the mean away from each score. And when I did that, I came up with a deviation score. So the deviation score is going to be in this column here. 2 minus 11.75 is negative 9.75. So I'm going to do that for each value, and I've already done that for you. But you would just put, this deviation or the mean in here, and you'll get a deviation score. So 2 minus 11.75 is going to give you a deviation score. 4 minus the mean, so I can just put the mu right here, just like that, but it's going to have a value of 11.75. And I do that for each value of n, and I'm going to come up with these deviation scores. Some are going to be negative, some are going to be positive. Not all the time you're going to have 4 positive and 4 negative, but when I add all my deviation scores up, I have to come up with 0. And if I come up with 0, I'm a happy camper because I did it right. All these values are correct. In one of my videos, I don't know if I shared that with you or not, but I made a mistake. And my mistake was my mean wasn't correct, and then this thing didn't equal to 0. So I was going, what the heck? I got to find that. I didn't know. So finally I figured out my mean wasn't even right, so none of this other stuff was correct. So once you do this and you add your deviation scores up and you get 0, you can go ahead and put a happy face there because you did all that work right up to that point. Now this formula tells me I have to square all my deviation scores. When I square negative 9.75, that's going to turn that into a positive number. If I square a negative number, it turns it into a positive number. So I get 95.062. That is what's called the squared deviation score. So I'm going to square each deviation score and put them into these columns, and I'm going to continue to add those up. Once I add all my squared deviation scores up, I will get something called the sum of squares. And that's what this score is down here. And that is going to be my numerator for my formula. Good deal. I've gotten a lot done so far. So my numerator for this particular formula is the sum of my deviation squared scores, or the sum of squares. So I've got 337.496. That is my numerator. Now my denominator is pretty darn easy to find because it's a number of observations I have. I have 8 runners who reported their mileage for the week. So 8 is going to be my denominator. So when I go ahead and I will go ahead and calculate that, I've got 337.496, and I'm going to divide that by 8, and I get a score of 42.187. So what that is my variance. So my variance is going to be equal to 42.187. Variance. Sorry about that. So that's my variance. Now, how in the heck do I get the standard deviation from that? Well, I got to take the square root of my variance. So what that looks like is the standard deviation is going to be equal to the square root of the variance. So let's go ahead and do that. So I have 42.187, and I'm going to take the square root of that. Okay, maybe I have to do that first. Square root of 42.187. There we go. So that shrinks that score down to give me a standard distance from the mean, which is going to be 6.495. So I have 6.495 standard deviations from the mean of 11.75. So what that tells me is I have that standard distance that will, encapsulate or incorporate all the data that we're talking about. So that's the standard deviation. That's how to come up with it. So it's pretty easy. And I've got a couple of videos that I'll share that I think I made a mistake on one that shows you how to do all this stuff. But that's the standard deviation and the variance. Pretty easy to find. The formula is a little cumbersome, but it tells you, step by step how to get that, and my little example shows you how to do that as well. So, the population variance, sigma squared, the sum of all your x's minus the mean squared over n. Which is exactly what we did there. And then to get the population standard deviation, I have to take the square root of my variance. A little cumbersome. With smaller data sets, it's not too bad, but once we do one of these examples by hand, I'm going to show you how to do it in Excel. Once you know how to do it by hand, you know where the numbers are coming from, you know where you're getting, the sum of squares, you know what sum of squares is, you know where those numbers came from, then we can start doing things with the computer to make it a whole lot easier. But I wanted to show you where those numbers come from, so you'll have, at least an idea when you say the sum of squares, you know exactly what that means, because we'll be using that a lot. All right. It determines the spread of the data. So what that means, the smaller your standard deviation, the spread is going to be more compacted. So if you've got a lot of variation, your standard deviation is going to be larger. So it determines the consistency of these variables that we talked about. So it falls within that. It doesn't really, account for what we call outliers, but what I'm going to talk about in the next video that I post, and I'm going to show you how to catch outliers using John Tukey's method of casting a net of interquartile range to catch those. So that's pretty cool. All right, population variance and population standard deviation, all that stuff that we talked about, all of it's good, and I'm happy with that. So there's another example just like I did on the board, so you can try that one at home, kind of neat. Oh, let's talk about sample real quick. Now, the only difference between population and sample is that I'm going to use a little bit different symbols. So, like I said, X bar is going to be the symbol for the mean of a sample. And lowercase n is going to be the symbol for what we call sample size. So our sample size is lowercase n, and to make some adjustments for not having the whole population, I have n minus 1. And what this means, I have what's called degrees of freedom. Very complicated concept to grasp. Not sure if I'll get into that because I could probably spend the rest of the semester talking about degrees of freedom. If you want a private lesson on that, come and see me sometime and I'll bore you to death. But I can do it, but it would take me quite a while to explain what degrees of freedom are. But basically what I have here, I have 7 degrees of freedom. because I have n and I'm taking 1 away from of n, I've got 8 in my sample size in this particular example. And if I take 1 away from that, I got 7. So I have 7 degrees of freedom here. And basically what happens is if I'm dealing with very, very large data sets, 1 is not going to make a big difference. But if I'm dealing with very small data sets, 1 is going to make a huge difference. So I have to make some kind of adjustments when I'm not dealing with the whole population. And this works really, really well. Because like I say, if I have a small data set, it's gonna, if I take 1 away from the denominator, it's gonna make a big difference with pushing numbers to, toward the mean.